Right, so A minus I lambda, in fact, very appropriately placed, because really that's what we're looking for. And you could actually just plug it right in immediately, but I'll write it all just so we can have a not red spots. So the I lambda, or lambda I, it matters not. And again, I've mentioned this many times. I prefer this variation of it because I don't have to worry about anything that's off the diagonal. I make enough mistakes as it is. Oh, and I already screwed it up. Look at me. Classic. Okay, so we have our characteristic matrix. Now, at this point, since we already know what one of the lambda values are, we just pop it in. So A minus 3I. And again, it's only the values along the main diagonal that we care about. So 1, 0, negative 1, 3, negative 3, 3, 2, negative 2, 2. All right, we want to set that equal to 0 because it's got to be A minus 3I times x equals 0. So times x1, 2, 3 equals 0, 0, 0. All right, feel free to cut out the fluff if you want. You can just jump right to the appropriate matrix, because again, you've already been assessed on solving homogeneous equations. We're just streamlining at this point. 3 by 4 is what it would be. Although this one actually is not. If you felt the need to do it by hand, the second and third row are scalars of each other, so you're in good shape there. Basically, it wouldn't be like one of those cases where after you spent the time to do it by hand, you wouldn't be like, oh dang, I just wasted half an hour, because it should only take you like 2 minutes. So that's the idea. Okay, I think I typed it in correctly. That was the plan anyway. Best laid plans of mice. Alright, so we have x1 equals x3, x2 equals 2x3, x3 equals itself. So x would be equal to x3 by 1, 2, 1. So the basis for the, well, can't even, like, I don't even know why I tried doing script there. The basis would be the 1, 2, 1. Because everything else would be a scalar multiple of that to make up your eigenspace. And the eigenvalues, so this one's, I mean, good and bad. I mean, eigenvalues are typically a little bit more of a pain to come up with, but typically, sometimes they're not. But we at least don't have to come up with the eigenvectors afterwards. Right, so progression, we have to get to this, and then we have to actually find where the determinant would be equal to 0. All right, so a minus I lambda would be equal to 5 minus lambda, 0, 0, 0, negative lambda, 0, negative 1, 0, 3 minus lambda. You know if something's triangular, to get the determinant, all we have to do is multiply down the main diagonal. This one's lower triangular. Could be upper triangular. It could be just completely diagonal, it doesn't matter. So we're in good shape here. Multiply down the main diagonal, and we will have our determinant. If you don't make that recognition, that's okay. You can still do it with cofactor. You're going to have a lot of zeros canceling things out. I mean, in the grand scheme of things, it's not the worst mistake to make, because there's kind of a nice little payoff for that too. You're like, all right, let me do the cofactor expansion. And you're like, oh yeah, 0 times this, 0 times that. Okay, a lot of stuff cancel out, so I'm just left with this. And then if you at that moment say, oh, I could have just got that by multiplying down the diagonal, it's like, okay, but it's not that terrible of a situation to be in. Right. So 0 is what it needs to be equal to. All right, so again, the eigenvalues create a matrix whose determinant is equal to 0, which forces us into a situation, whatever space you're in, it presses you down onto a single line. And what that means is that anything that involves related to any of these eigenvalues is going to give us a vector that is a scalar of whatever our basis vector is. Right? So solve lambda equal to 5, 0, and 3. Without the requirement that we have to that we need to come up with eigenvectors. So let me stop there. Yeah, sure. By the way, in this